Drawing Lewis dot structures for simple molecules. In this problem, it says, which of the following is the correct Lewis dot structure for H2O, dihydrogen monoxide or water? So, we have four options here, and we have to figure out which one is the correct Lewis dot structure. So first, we have to draw the correct Lewis dot structure so we can see which one matches up with our correct drawing. So when we're writing the Lewis dot structure, we write kind of a skeleton structure for the compound and then start adding the valence electrons that it has to have. So here we know that there are three elements involved, and so O, H, and H. So notice that they have a specific shape based on the electrons that they have, and this is discussed when we talk about the Vesper model or the valence electron repulsion model. So here we're going to talk, but here we're just dealing with Lewis dot structures, so we won't worry about the shape too much. But first we have to notice that we do draw lines here between this valence electron, the one valence electron that hydrogen has, and the valence electrons that it's going to share with oxygen. So what we're first going to do is draw kind of a shape around it, and we usually put the least electronegative atom in the central position. However, we usually put hydrogen and fluorine on the end. So these are the end positions, this is the central position, the center of the Lewis dot structure. So here, I'm just going to draw a line connecting the O and H, and this O and this H here. So we have to count the total number of valence electrons present in this molecule because we want to make sure that we have the correct number of bonds going on here. So first, we have to make sure, so oxygen has 6 valence electrons because it has 6 valence electrons. So oxygen has 6 valence electrons because it's in group 6, and that's what its electron configurations show. So 6 valence electrons, we have 6, and then we have 1 from H and 1 from this H. So that's H has 1 valence electron, and since there's 2 of them, that means we have 2 valence electrons total. So in total, electrons. So we have 2 valence electrons, 6 valence electrons here, so that means we have a total of 8 valence electrons. And this should sound good because remember, when we want the atoms bond together because they want to be stable and they want to have 8 valence electrons in their valence electron shell. So what we can see here is we already have 2 here, H and O. When we see this line connecting them, we should assume that they are sharing electrons, or they are electron has been transferred. That's why they're connected. So we should count this line as 2. So 1, 2, 3, 4. So we have 4 valence electrons here, but we know that there are actually 4 more valence electrons floating around. So there's 4 in the bonds here, this bond and this bond, but we know that there are 4 more. So we draw them as pairs of dots. 1, 2, 3, 4. Because they're not being shared or connected to anything else, and they're happy where they are. So we have 1, 2, 3, 4, 5, 6, 7, 8. And notice that oxygen is very happy because it has 8 valence electrons around its valence shell, and H usually gives up an electron, so it's happy, and this H also is happy because it's given up an electron. So this is the correct Lewis dot structure for H2O. So when you draw a Lewis dot structure, you put the least electronegative atom in the center, and then you draw the lines connecting it, forming a skeletal structure, and then you count the valence electrons to make sure that they have the correct number. So let's see, A here, O, oxygen, 1, 2, 3, 4, 5, 6. Only 6 valence electrons in this one, and we know that's incorrect. B, we see that it's 1, 2, 3, 4, 5, 6, 7, 8, exactly matching the picture that we have here. So B is the correct answer for this problem. C shows us only 1, 2, 3, 4. Remember the lines count for 2 valence electrons, only 2 lines, so that shows us we only have 4 valence electrons interacting here, and we know that's not true because we already know that oxygen has 6 valence electrons. Here, notice that they have 1, 2, 3, 4, 5, 6, valence electrons around oxygen. But it's a kind of a trick answer because remember that this line counts for 2 valence electrons. So in total, this whole structure has 10 valence electrons. And to have 10 valence electrons, we would have to make sure that this would have 2 negative, meaning it has 2 extra valence electrons. But it is not 2 negative, so that means D is actually wrong. So B is the correct answer for this problem.